back to the afternoon session. So it's my pleasure to introduce Eli Fieldsteel to the symposium. So Eli is a composer specializing in music technology with a diverse history of interdisciplinary collaborations. So he's highly recognized for his work. Just to name a few recognitions, from the Frank Ticheli competition, he was awarded in 2014 the James E. Croft Grant for Young and Emerging Wind Band Composers, and he won first prize in the 2012 ASCAP SAMUS Student Commission competition. His music has been performed widely and internationally, including from groups like the Dallas Wind Symphony, the North Texas Symphony Orchestra, the Kawagoe Soa Wind Ensemble of Tokyo, and the University of North Carolina Chapel Hill Wind Ensemble. So Eli's music and research engages with the intersection between music technology and performance, focusing on human-computer improvisation, interactivity, and sensor-driven music. Utilizing new technologies and real-time environments, his works are highly gestural, expressive, and richly detailed. As an active collaborator, he has worked closely with dancers, choreographers, lighting designers, architects, and video artists, resulting in a variety of unique instruments and site-specific installations and performances. He is fluent in several music programming languages and maintains an active teaching presence online through a well-trafficked series of Super Collider tutorials. So Eli, welcome to ICFO and the symposium, and we look forward to your presentation.
Thank you. Yeah, hi, it's great to be here. Thank you, Raiko, for inviting me and for organizing this symposium. So as you can probably tell from that introduction and my bio, I'm a musician, a composer by trade and by training. And when Raiko reached out to invite me to this symposium, blending music composition with quantum physics, frankly, I was a bit surprised because I do not consider myself a quantum scientist. Some of my work is perhaps science adjacent, but a lot of these talks have been really new to me, and I'm finding them all very interesting and exciting. So the degree to which the presentation I'm going to give overlaps with quantum sciences is probably a little bit coincidental, if anything. But yeah, it's just really been enjoying these talks so far. So yeah, I'm a teacher of music composition and technology at the University of Illinois, where I direct the experimental music studios, which were founded by Lejar and Hiller in 1958. I know we've seen his name come up in a few presentations already, so I'm pleased to see that the sort of overlap in these circles as well. So I'll be presenting. I suppose you can call it a musical instrument, but probably a little bit more accurate to call it a musical control surface or a control interface that uses photoresistors to detect light and generate data, which is then mapped onto sound. I know you sort of can't see it. I've got some photos I'll show. It lives in this big, heavy road case to my left here, and if anyone would like to help me carry it back to my hotel, I will buy you a beer. Okay, so the structure of this presentation will be as follows. I'll share some photos to contextualize this project and my work and sort of how I arrived at this project. We'll then at that point take the lights down, and I'll sort of give a demonstration of the basic operating principles and capacities of the device. I'll then perform a composition of mine. It's about 6 minutes or so, and then I will unpack and dissect that composition and kind of just to show how it was structured and how it uses the sort of data generated by light sensors. And then briefly talk about some limitations and future directions, and hopefully we'll have some time for questions at the end. So as I said, a composer by trade, and some of my accolades from earlier on are sort of for pure acoustic compositions, for wind band, orchestra, things like that. And then when I began my graduate studies at North Texas and UT Austin, I started to get involved with music technology in a variety of ways, and sort of the math and science aspects of music composition. So I started working with sensors and getting involved in these interdisciplinary collaborative projects. This is an image from a collaboration with a choreographer and two dancers. Each of the two dancers have a Nintendo Wiimote attached to their limbs, one on one of the legs and one on one of their forearms, which is why they have these colored bands to sort of conceal the device. And this piece just basically taking that motion data and then finding interesting ways to map it onto sound. And it was a new direction for me, because when the dancers don't move, nothing happens. So the piece is very intimately connected with the movement of the dancers, rather than having composed some sounds and then sort of inserting the dancers into that framework. This is me performing up in New York City, an octaphonic composition using a pen and tablet controller, where I sort of take the X, Y, velocity, tilt, pressure, and things like that coming from the pen, and mapping that onto sound as well. This is me performing at Ball State University in Indiana with a pair of homemade sensor gloves, which each have an accelerometer, a two-dimensional accelerometer on the back, and a light sensor, a light-sensitive resistor on the front. And this was a quadraphonic work where I can sort of move sounds around the space quite fluidly with my hands. And in my current position at the University of Illinois, I advise music technology students and students who are pursuing a Bachelor of Science degree, which blends computer science and music, on their senior capstone project. So Casey on the left has built a sensor glove of his own, which relies on flex sensors. And Wataru on the right has built a sort of musical step pad where you can sort of apply pressure with your feet and your body on that device and produce musical results. And all of that laid the groundwork for the most recent project, the one which I'm presenting today, which is a musical device which I've called LightMatrix. It is a square grid, 16 by 16, so 256 total photoresistors, which are arranged in this sort of square grid arrangement. And they detect changes in ambient light. They're all sort of independently operating, and the microcontroller, sort of on the right-hand side, digitizes that data and pipes it out on a USB cable to a computer, where it can be arbitrarily mapped onto sound, in my case. But really, it's just numbers, so it can be applied for visuals or sort of anything else which is capable of accepting that kind of data. The circuitry is, at the heart of it, really quite simple. This is a diagram that you will probably see if you go on the internet and Google, introductory Arduino project, where you have like one light sensor and one 10K resistor, and it's just a simple voltage divider circuit. Now, my area is composition, so the sort of electrical engineering aspect is very, it's something I'm still learning and still understanding. But essentially, you have a light source, and as you cast a shadow, that darkens the experience of the sensor, and that's going to lower the voltage, and you shine a light on it, and that's going to increase the voltage. And all you have to do is really digitize that, and you have numbers that can be used with a programming language. So at my university, I sort of wrote a small grant and bought some equipment to start building a basic prototype. So a bunch of testing, measurements, and just starting to put everything into place. To help make the prototype building process more enjoyable, I was sort of live streaming it on the internet over the summer. This was back in 2018 or 19 or so. And I one of the earliest problems I encountered was, okay, I'm going to have 256 independent sensors all generating data. How am I going to have 256 cables? That would be outrageous. So I used these multiplexers, and the original concept was to take 16 channel multiplexers, each of those capable of accepting 16 signals. And what a multiplexer does, for anyone who's not familiar, is it basically encodes multiple signals along a single cable. So it's, you can have sort of multi-channel data, but you don't need many cables. And the idea was that I would use one of these Arduino Megas, which have 16 analog inputs, to basically condense 256 data streams down to 16. I also had some composition students who were actually very good carpenters, and had some help building a box in which these would live. I did make a lid and drill all these holes, only to find that it was actually challenging, if not impossible, to actually get the lid on the top so that all 256 photocells would go through. So it was a big learning process building this initial prototype. I actually didn't even use the lid. I just let it sort of sit as it is. So this is as far as I got with the initial prototype, and I'm going to zoom in. Just so you can see the nightmarish chaos that is this prototype. It was around this point where everything was working properly. I had 7 out of the 16 rows completed, and several kilometers of insulated wire. And I thought, okay, this is working and it's sound, but I cannot travel with this. I can't even really move it down the hallway, because if it gets bumped, everything's going to fly out, and so yeah. I thought there was a next step in the progress. I am very fortunate to teach at a university that has an incredibly strong computer science and engineering campus, and all of the engineering students in their final year or final semester take a class called Senior Design, and they're all required to propose projects, large-scale projects, which they then bring to completion. And the TAs for this class will reach out to various people and invite people to present ideas. And so I got my foot in the door and brought my janky prototype and demonstrated it for a class of about 400 students. And a lot of them were very excited about it. And two students in particular, Alonzo Marsh and Sean Lee, came to me and they said, we have a lot of really good ideas which can improve this. We'll design printed circuit boards, and they just had a lot of really sharp ideas that I don't think I really would have came up with. So they put together, I'm just excerpting parts of their much longer proposal, just outlining the power management and the sort of multiplexer design and the printed circuit board configurations and things like that. So all of this came together, and they had the PCBs manufactured. They did a lot of the wiring. I had this road case purchased and sort of fitted to the device because the dimensions were known now. And this is the sort of the finished device in one of the studios at the Experimental Music Studios at Illinois. This is a setup for an earlier composition, not the one I'll play today, but it's an earlier composition for the Light-Matrix. It's a duet involving tenor saxophone. That's what the microphone on the right is for. This piece is called Depth of Field. It's been performed a couple of times where the computer is generating some sound, autonomously, and the sound can be shaped and sculpted and manipulated by interacting with the Light-Matrix. But it is also processing the tenor saxophone signal, which is captured. So I can, by covering certain parts of the board, I had these blocks that I could place on the board to keep parts of it covered and in a sort of hands-free manner. I was able to do things like infinite reverb effects and sort of infinite echo effects, and it turned into this really kind of nice and immersive piece. Here's an image from the dress rehearsal with the saxophones in the background. Excuse me. Another deployment of this control surface was at a festival that a friend and colleague of mine named Jake Metz hosted at the Independent Media Center, which is in downtown Urbana. And it was called Immersion Fest. And it was essentially just an open call for works for sound and visuals and multimedia, cross-disciplinary things, which were in some way, shape, or form immersive. And the centerpiece of this festival was this 18-channel geodesic dome that Jake constructed, and one of the calls for works was pieces which would involved this dome, and so I had the LightMatrix set up in the dome and presented a version of the piece I'm going to perform for you, which was meant to be sort of an installation where passersby could come and interact with it. And the sounds were mapped not in stereo, but actually an 18-channel version of them, so that when you wave your hand from left to right, the sounds would sort of traverse the dome space, kind of in an analogous fashion. So it was a lot of fun. It was very successful, and it was really nice to sort of from a corner sort of watch what people would try to do as they'd approach it, and everyone kind of had a different sort of sense of intuition of what you should do with the device. And I tried to design the sounds. It's similar in a way to one of the slides we saw on Rodney Duplessis' talk, which is that I didn't want the data mapping to be so simple that it became a sort of clinical exercise where it was like super obvious. But I also didn't want to take too many liberties for fear that the relationship between the data and the sound became invisible or superficial or something like that. So we'll move on to the next phase of the presentation here. So I will have a sort of kind of a discussion and demonstration of the basic operating principles of the device. So if we could take the lights down to 0. This will just take 30 seconds or so to set up. So this is a program that I wrote in Super Collider just allow me to easily kind of demonstrate the device. And all it really does is listen to the serial port for incoming data. And here is the data in its most raw form, which is an array of symbols, which are numbers and commas and spaces and things like that, which needed to be further processed into an array of proper integers, which looks like this. Are those numbers large enough for folks in the back? Should I increase the font size? Yes. Is that a thumbs up, they are good, or thumbs up, make it larger? Okay, yeah, good. So the analog to digital converter on this Arduino board is a 10-bit converter. So it is taking the voltages of all the individual photocells, which is between theoretically 0 and 5 volts, and it is turning them into integers between 0 and 1023. And the higher the values, the brighter the light. And one thing you can see, sort of, they're all sort of moving, so that tells me that the device is working, and it's there's like very, very subtle changes in the ambient light. But you can also notice that there's kind of a problem here, which is that despite the fact that they're all receiving, they're all under the same light source, and even two cells which are kind of right next to each other have values which are significantly different. There's some in the sort of high 600s, some in the lower 500s, and So that was sort of the first problem I set out to solve. If we just print the minimum, the maximum, and the average, it's data which is not really easy to deal with from a musical perspective because it's so wide in terms of range. And I believe this is just due to the fact that these are physical analog devices and that there's just natural discrepancies in the data. You know, they're not sort of robotic, digitally perfect devices. So the solution here was to take a snapshot of all of the raw values at time 0, and then from that point on, not actually work with the raw data themselves, but work with the difference of the raw data and that initial snapshot. So whatever the initial snapshot is, the board then says, okay, that is equilibrium, or that's our baseline where everything is sort of 0, and negative numbers are dark and positive numbers are light. So that is, and then once you have that, I need to do this first, I think. Actually, I think I might have to go back a second and start at the beginning here. Right. Stop. Then we normalize. Yeah. And then once we have the raw data, we can very easily normalize them to a range of 0 to 1 or whatever we want. And when I was first building this, I thought that 1 would be the brightest possible thing and 0 would be the darkest possible thing. In this current version, I just have the one light source, and I'm performing with no mechanism to actually brighten the environment. So I could have just normalized this to 1, I suppose, but instead I normalized it to about 0.75, and this then makes the data much easier to work with. And then the final thing I did before I started playing around with sound was to build visual representation. And this was really essential for just making sure, hello, that I had all of the array was structured correctly. I have a bottom row down here, which I can just run my hand over. So it's all sort of live and working and sort of like a 2D Minecraft sort of thing. Yeah, so, and you can see the normalization really helps because the shade of gray is really quite uniform across the device. And so, if I were to take a light and shine it, on the board, it would get brighter. In fact, I can probably do that real quick. Yeah, that's my cell phone flashlight. So this was all very exciting because now I knew I could actually start making sound, and I have a brief sort of audio demo here, and I will go through parts of this. I'll probably skip a few parts, but here's we have a sound that's playing. We don't hear it because the amplitude is very low, and we can hear it just a little bit. And just as a very basic demonstration, I am mapping the darkness of the bottom left photocell to the amplitude of the sound. So I can just cover it up very gradually. And it's responsive. Nothing is going on over here. So just to demonstrate sort of the independence, it's just this one in the corner. And here's an example where I've done the same thing with 16 different pitches for the 16 photocells on the lower left printed circuit board. So. So it lends itself very, very nicely to improvisation. Just, in terms of just being able to design a sort of data to sound mapping, and then you can just kind of play. let's see. So there's it's quite easy to load samples into Super Collider. So this is a sample of a prayer bowl being struck. And here we go. We can just assign a unique transposition of those samples to, in this case, not individual photo cells, but what I've done here is written an algorithm which averages the 16 cells on one board, and when that average falls below a certain threshold, it will trigger the sample, and then when the average falls above that threshold, or rises above that threshold, it will reset the triggering mechanism. So we can sort of just bring a hand over one of these. If we do it slowly, right? Sort of takes enough of the cells need to be darkened. How is the volume okay? Is it too loud? Yeah. Okay. Good. Yeah. We have sort of a wind chimes thing happening here, and just to sort of make sure that it could be done, here is a microtonal version which actually does map all of the, so each individual photocell to an individual sample. So if we just kind of go across the bottom. Actually just a little bit loud for me, so I'm gonna turn that down by 6 decibels or so. And there's a very fun comb filtering effect that happens if we shut the light off. Because they all trigger at the same time, and they're all sort of uniformly detuned, geometrically. So anyway, it's just there were a couple of fun discoveries in the process of making this sort of sandbox style program. Let's see. So I think what I'd like to do now is move on and perform a composition, which is called impulse curve, and then I'll sort of unpack that and talk about the inner workings of that piece. So again, this will take just 30 seconds or so to just calibrate and get it set up. think the gain is too high on the mixer. I'm just going to adjust this real quick. Oh, well, I can't really go into too much detail, but that I think that might not work for sort of code-related reasons. Yeah, I'm sorry. Yeah. Thank you. So the the process for composing this piece is you might have been able to hear from the performance that there are much like I was doing in the demonstration sandbox patch. I was just kind of writing or composing simple sounds that onto which data from the light sensors could be mapped, and that's essentially what I did in this piece as well, just on a sort of more in a more complex and nuanced way. So there are three soundscapes in total, and the way the piece is designed to be performed, it's sort of non-deterministic. Each individual soundscape has elements of randomness kind of built into it, not quantum randomness as we've been talking about at a number of these presentations, but more traditional computer randomness, which is ultimately deterministic, but random enough for humans to feel satisfied. And most humans anyway. And the first soundscape is this one, which is just composed of extremely aggressively bandpass filtered noise, many copies, many filters, and all of the center frequencies of the filters are aligned with pitches about 70% of the time, which fall into this diatonic system where we feel that there's a sense of tonal stability. But just to keep things interesting enough, as you listen to this, you'll hear 30% of the time or so notes which are, I guess, from a diatonic perspective, wrong notes. And this is just like a sort of a balancing act for me, just making sure that we don't really want a C major triad for 6 minutes. That's a little bit much, perhaps. Just gets a little boring. And the nature of the interaction with this sound is it's sort of on one end of the spectrum, and it's actually taking all 256 values and just averaging them together. So it's essentially treating the board as one big photocell, which can be kind of partially covered or completely covered. We're getting some sort of distortion in the system here. It's not intentional, but so that's the pitches themselves are not actually controlled by the degree to which the photosensors are being manipulated. The pitches are kind of on an autonomous, infinitely generated routine of sorts, and but it's when more and more of the photocells are darkened, the bandpass filters widen and also the amplitude increases. So we have this kind of smooth transition from discrete pitches to just kind of flooding the speakers with noise. The second soundscape, the one which has these kind of bell-like sounds, which when there's no interaction happening, it's all pretty sparse. You just hear a couple of bells, once every few seconds or so. Right. And this soundscape, in terms of interaction, falls a little bit on the middle of the spectrum, where it's actually 16 processes, and each one is only looking at a vertical, sort of a vertical column of photocells, and it is averaging that data. And when that data is, when that column is dark enough, as it darkens, the density of the bells will increase, and they are also spatially mapped across the stereo field. So when I'm sort of over here, we get, you can turn that up a little bit more. I'm not really sure why it was distorting. But yeah, so and this motion I'm doing here is completely superficial. Yeah, I can just hold my arm over it. Well, so there's a little bit of performance aesthetics being mixed in here. But which I think is on the one hand a little bit silly, but also I think there is some value in that as like a musical performance. And so as I'm sort of in the middle, you can hear the bells are sort of centered. And over here they're on the right. And the last soundscape, which I think is probably the most interesting one, is built off of like very high frequency, very short duration kind of grains and bursts of like impulse train waves and things like that. They're meant to sound like little glitches in the system, And this soundscape is sort of at the other end of the spectrum in that it is highly active when the smallest number of photocells are covered. So if I just sort of bring my hand towards the edge of the device, and I'm just covering one or two of the photocells in the very front row here, it sort of wakes up and starts to do things. And this one is also a little bit temperamental, I think, just because of the way I have it coded. It doesn't always respond immediately. Sometimes it takes a half a second or so to kind of wake up. But I sort of like that about it. It feels like the device has a kind of a personality where it's sort of got its own musical decisions that it's making, and not always listening to me. And in that sense, is kind of a realistic collaborator. So I designed these three scapes so that I could reasonably well activate them independently. You know, I can do these sort of big gestures which affect the first soundscape. I can be sort of vertically oriented with my gestures, and that's going to sort of activate the second soundscape. And if I do a very, very little bit of interaction, I can activate the third soundscape. And they can all be, you know, on at the same time, you know. And you know, I think it makes for sort of a nice mix. And so in performance, as I've just done, I sort of have a rough trajectory of the things I'd like to do and when I'd like to do them and how long I'd like to do them and the different combinations, which I sometimes follow and I don't always follow. But when it was installed in the dome for Immersion Fest, I just turned everything on and just let it run for, you know, an hour, and just people would come and play with it and things like that. So that's essentially the. I should also add that I am definitely you know, cheating a little bit, and I have this MIDI controller here, the sole function of which is to allow me to activate and deactivate soundscapes, and also activate and deactivate whether they are interactable. Now, in the past, I have done this with the LightMatrix itself by encoding, you know, very specific gesture recognition algorithms into it. The other piece for tenor saxophone, in order to move from state to state through the piece, from beginning to end, what I needed to do was cover two very specific photocells without covering the photocells around them. And that looked sort of like this. Which I thought would be covert, but everyone, and you know, people would come up and say, "What was that thing you were doing when you were?" You know, I didn't hear anything. And so I think it had the opposite effect. I thought it would be a subtle thing, but it turned out to be kind of distracting for the audience. And they were expecting to hear something happen. There wasn't always something obvious that would happen there. So in this particular case, I opted to go for just a MIDI controller. I suppose I could do the same thing with maybe a foot pedal controller, or you know, I just need to have some way of making large-scale performance timing decisions, and that's what I sort of went for here. So the one kind of, sort of moving on to the tail end of things here, and just kind of the limitations and future directions. The pieces that I've composed for the LightMatrix so far involve this. You know, light source, which, you know, I use because it's a reliable amount of light. You know, if I rely on the lighting of a space, that's going to vary quite a bit, and in some situations, the device will really not work very well. And you know, I can bring flashlights and add light, but I've composed these pieces so that it's really just a sort of shadowing mechanism. So I'm just casting shadows and not actually adding more light. So in that sense, these pieces are unipolar, I suppose you can describe them, where the lighting can only change in one direction. That's a little bit limiting. It's not extremely limiting, but it does sort of make the piece sort of one-dimensional in a sense. So and another limitation related to that is that if I want to cover a photocell in the middle of the board, I cannot do so without casting an arm shadow over a bunch of other photocells. So I can't play this like a piano where you can press any key or sort of any number of keys at will. So you know, if I want to do individual things, I have to kind of map it to the outer ring of photocells. Now, if what I'd like to do, which I have the materials, just I'm sort of making my way through the process, is I have a pair of bicycle gloves, and I'm going to sew LEDs to the center of the palm and use conductive thread and have a little battery pack on them so that I actually have light gloves that I can actually direct sort of focused light onto the board. And that's nice because I can just make fists and the light goes away and I can open my, so that'll hopefully turn this into a more flexible performance conduit, just being able to get bright and also dark. And I think that'll add an interesting musical sort of dimension. So that's sort of what's next for this. But I think there's a lot more to explore in terms of the musical potential. So I think that's sort of all I've had prepared in terms of lectures. So what I'd like to do is just bring the lights back up to 50, and I'd be happy to take any questions. Thank you. That's a great question. I don't think I've given a single presentation of this instrument without getting that question. It's a good question. I think it is difficult to overstate just how non-user friendly and intuitive this device is to use, especially considering that if you plug it into a computer, it really doesn't do anything. You need to write a program which receives the data and maps it onto sound. This device is actually completely sound agnostic. It doesn't know anything about the receiving device's use of the data. There's no MIDI, there's no OSC. It's just sort of raw ASCII data flowing in, and so I have to that's sort of why I have two separate programs here. One is to just receive the data and parse it and process it into sort of numbers, and the other is all about synthesis, and it's actually the sort of musical composition part of it. So in order to make this commercially viable, I think there would be a lot more work that has to be done, which almost certainly could not be done by me because I am not an entrepreneur. I'm an academic. So it would need to come with some sort of hardware-software unit which comes with a bunch of presets so that somebody who really doesn't know anything about this kind of thing could use it in a satisfying way. So in its current state, no, I think it's not something which could be easily commercialized. But I suppose if I found the right collaborator, it could turn into something like that. Yeah. Yeah, that's been suggested by. I've heard that suggestion before, and I think I've considered it, and I think the easiest way to do that at this point is to actually take colored gels that you put over, over lights in a theater, and actually cut them and maybe apply them to the surface, so that in that way those gels would filter out certain lights. So then I don't. It's something I've thought about, but I haven't actually sort of played around with yet. I'd need to buy a few things and see if that would work. But I think that would definitely make for a very an even more engaging kind of performance with not just gesture and sound and light, but also color. It'd be very exciting. But no, so far I have not explored that avenue. It is on my mind, certainly. I'm the but I think it's important to keep in mind that the only reason my knowledge of quantum sciences is greater than zero is because I've spent the last day and a half here at this symposium. So it's all still very new to me. I look forward to conversations. Which I don't mean to they will be on a very basic level if you're talking to me. I'll need I'll sort of a 101 style class on just what things are and how they work. But I am certainly open to sort of intersections between this work and quantum sciences, which are which amplify both disciplines in ways. But I think I have a long way to go. Mhm. Yeah, that's a great idea. And when this was presented at Immersion Fest, there was another installation which was a grid of. I might be slightly misremembering, but it was a grid of each unit was a photocell and an LED, and they were sort of tied together and sort of. So it was a sort of self-feedback system, whereas sort of as you covered it up, the light would come on, and the light would sort of spill onto neighboring photocells, and so you could just sort of make a quick gesture, and then it would kind of dance and sort of ripple outward in interesting ways. So I imagine something like that could be done by just coupling each photocell with a light source and having them be and being able to play with that relationship. So as the as it gets shadowed, the light will come on, or vice versa, or something like that. And I think that could make for a really compelling sort of visual installation. Maybe pairing that with sound as well. And when you say what are they, do you mean like the sort of specifications of the actual cells? I can't rattle off sort of specification sheet data on the top of my head. I mean, I bought them in a large pouch of 1,000, and I mean, probably you have to imagine somebody who doesn't really know anything about electronics searching on Amazon or whatever for photocells. Yeah, my experience just from interacting with this instrument, sort of on a musical level, is that the photocells are fairly sensitive in that I can sort of put my hand and make these what feel like very microscopic movements and have the changes be musically substantial. Much in the way that when you watch somebody sort of bow a violin and you can see like the very minute changes in sort of hand position, things like that will produce similarly subtle musical results, but audible nonetheless. But I also do feel like they could be a lot more sensitive. I'm sure there are devices which are designed to be sort of hypersensitive. But just looking, we saw the numbers sort of from the raw data. You can see that just even not really interacting with them, they just kind of fluctuate by a few hundredths of a volt or something like that. Yeah, thank you all very much.